Okay, so welcome everybody. Our speaker today is Philipp Schönhöfer, and he's from the University of Michigan, and he's going to tell us about rationalizing Euclidean assemblies of hard polyhedra from tessellations in curved space. Okay, Philipp, over to you.
Yeah, thank you so much, Adil, and also to the other organizers for inviting me to give this talk. I really enjoy this whole webinar, so it's a really pleasure for me to give a talk as well. And yeah, so like Adil said, I'm Philipp Schönhöfer. I'm a postdoc in Sharon Glotzer's group here at the University of Michigan, and this whole project is also in collaboration with Sharon and also with Kai Sun and Xiaoming Mao in the physics department here in Michigan. And basically the idea behind this whole project was to have a look at self-assembly. So here it is more hard particle self-assembly, but self-assembly in general from a very different perspective, namely in terms of curved space. And I hope that in the progress of this talk, you will understand what I mean with this different perspective. But to put everything into into context, I really want to remind all of you, even though I don't think this audience needs this reminder, but still, that nowadays we can generate a lot of different structures based on self-assembly and specifically colloidal self-assembly, from very simple crystals to very complicated atomic crystals. And this is just because the synthesis techniques has developed such that we can create different shaped particles. We can create particles with different anisotropic surface chemistry on them, which can be functionalized with DNA or polymers, and so on and so forth. And we can get closed structures and open structures and all of them. But the interesting part of this is that often, to create these kind of crystals, we often don't even need this degree of complexity. We can only look, for example, at one specific attribute of a particle, for example, its shape. And Sharon and also many others in our community have looked exactly at that aspect of just entropic self-assembly, where the particles just interact via their excluded volume, and where entropy maximization gives you the result in the final self-assembled structure. And also here, like I said, you can generate a plethora of different crystal structures, which go from very simple crystals like FCC and HCP crystals to very complicated. And here I, for example, have show the clathrate, which is a system which has hundreds of particles in their unit cell. And again, this is just via entropy maximization and via the shape of the particle, that based on that they want a self-assembly into this crystal. And a shape family which really nicely shows this whole range of complexity is even maybe the simplest family of shapes, and these are the Platonic solids. So when we, for example, look at the self-assembly of the Platonic solids from tetrahedron, cube, octahedron, icosahedron, dodecahedron, we can see that we get, again, very simple crystals, like, for example, the FCC crystal, where each particle individually where the environment of each particle, we have only one environment for each part of each particle in relation to their nearest neighbor. But we also have like very complicated crystals, like the beta manganese structure, which has two specific Wyckoff sites, which means that there are two specific local environments within this crystal, or even very famously the quasi-crystal, which self-assembles when you put tetrahedron, or look at the self-assembly of hard tetrahedra into the system. However, a very big problem of self-assembly still is that looking at the particle shape alone, it's really hard to predict what kind of crystal they will form if you don't try it out in experiment, or you use like numerical methods like molecular dynamics or Monte Carlo simulations. And even like predicting the particles from a packing perspective often doesn't give you the right result. So sometimes it is the right result, for example, for icosahedra, where you have like this FCC or the rhombohedral in the octahedron, which is where the self-assembled structure is the same as the densest packing, for example. However, for tetrahedron here on the left or the dodecahedron on the right, this is not the case. Here you get vastly different crystal structures. So packing, at least in Euclidean space, might not give us the right idea what kind of crystal structures can self-assemble by entropy maximization. And the problem, of course, is that the particles can't really perfectly tessellate space. So there's no real obvious solution. The only exception, of course, is the cube particle, because when you try to perfectly pack the system, you can 100% fill space by just placing them into a simple cubic lattice. And also entropically, it makes sense that they want to form a simple cubic crystal as well, because the simple cubic crystal gives you these very favorable face-to-face alignment. So inspired by this cube system, we were thinking about how can we maybe bring all the other particles of the Platonic solids into the same condition as the simple cubic, where we have the least amount of geometric frustration and the least amount of gaps for this self-assembly. And the idea we had is basically curving space. Because when you think about how can you get rid of this geometric frustration and gaps within a crystal structure, for example, one way is, of course, curving space. So here in the top layer, this means just if you have like triangles which don't fit perfectly and they form gaps, what you can do is to just pop into the third dimension and then make them align. And so then you have like a system without any gaps. And you can do the same thing in 3 dimensions, where you go instead of from tetrahedra, for example, where you go instead of from 3 dimensions into the 4th dimension and then make them align that way. And that introduces space curvature to the whole system. And luckily for us, when we look at all these Platonic solids, we can identify exactly these kind of curved crystals for each of the other Platonic solids. So, for example, for the icosahedra, we can identify a tessellation in H3, so in hyperbolic space, where the particles perfectly align with each other and where they fill space perfectly. So here it's on the top left. And for the octahedra, dodecahedra, and tetrahedra, we can find tessellations on S3, so on the 3-dimensional surface of a hypersphere, which tessellates space, like the space band perfectly. And here, just to let you know what I did, because, well, 4 dimensions is always hard to visualize. So what I did is I represent these as stereographic projections, which means that in the center, the cells are more deformed, and if you go to infinity, they get even larger. But you have to imagine that each of these cells have the same volume, and just because of the projection into 3 dimensions and then into the flat 2 dimensions, it looks like they have they have different volume, but overall, they the particle I look at a system of equal volume cells, basically. For the rest of this talk, I'm really interested in looking into these tessellations in S3 more precisely. And the question now is, can we use this kind of space curvature to regulate the geometric frustration to obtain locally optimal environments also in self-assembly? So we know that for in S3, when you curve space, that you can get perfect tessellations in terms of packing, but is this also true for self-assembly? And here, asking these kind of questions, I'm in company with like other people already before me, not at least in hard particle self-assembly, but also in terms of self-assembly itself. So for example, Alex Treviset looked at like Frank Caspar phases, and he already noticed like some sort of relation between the Frank Caspar phases and the local environments in Frank Caspar phases and in curved crystals, or for example, the formation of tetrahelices can be traced back to some sort of curved crystal. And also Randy Kamian looked at like liquid crystals, which can form these kind of phases, which can be traced back to Hopf vibrations, which is also a concept from curved space and curved spherical space. But I want to go even one step further and look at this in a very more general way for self-assembly in general. Okay, so how can we now answer these kind of questions? So these questions are mostly two questions, because one of them is basically, can we tessellate, can we create these kind of curved crystals and these tessellations also entropically? And then the second question is, if we can create them entropically, what can we learn from them about self-assembly in flat space? And for this, I performed hard particle Monte Carlo simulations on the three-dimensional hypersphere surface. So basically, this is the two-dimensional analogon where I placed a number of particles on the hypersphere surface. And then the only rule is that the particles are not allowed to overlap according to their shape. And then I slowly reduce the hypersphere radius by applying a pressure on the system, and then look if the particles assemble into a certain curved crystal or not. And like I said, because we only are interested in this project on spherical systems, I will focus on the dodecahedron, the icosahedron, and the tetrahedron. And you will see that I always show the shape on the right top, so you can always know which particle I'm actually talking about. So, okay, then let's start with the first particle. And the first question, are tessellations also entropically favored? And for this, I first started with dodecahedra. So I placed 120 dodecahedra on the surface of a hypersphere, so curved surface, and then slowly compressed the system. And you can see in this video, for example, that first of all, it's like in a very gassy phase, and the particles are just randomly distributed. But at some point, at some density, the particles start to align and form these kind of perfect tessellations when you compare it, for example, to the perfect so-called 120 cell structure, as you can see here. And also, when you look at the equations of state, you can see that the particles at some point will phase separate in terms of a first order phase transition into an ordered structure. And also when you look at the radial distribution functions here shown on the right, you can see that so this is the top one is the radial distribution function in terms of the center of the particles. And you can see that they show these kind of delta peaks, which can be traced back to the 120 cell crystal, which is the perfect tessellation. And also when you look at the vertices, so we look at how the vertices are distributed in terms of the radial distribution function, we can see that we get the dual lattice of the 120 cell, which is the so-called 600 cell. So we can really see that they indeed also entropically favor this 120 cell packing. What we can also see, which is pretty interesting, is that we apparently get also a rotator phase in this system, because the radial distribution function in terms of the center forms these peaks first before you can see any orientational order. And this is also in accordance with earlier studies in the 90s by Sadoku Moseri, who looked at numerical studies on spheres on S3. And there they also saw that the ideal packing for spheres is also around 120, which means that also the sphere, and because the dodecahedron is also very sphere-like, this 120 cell is also entropically favored, and therefore it makes sense that they first align translationally or form this crystal translationally before they go also order orientationally. So okay, the dodecahedra seems to self-assemble into the 120 cell. What about the octahedron? So here I have the same protocol. Basically, I put 24, instead of 120 particles, I put 24 particles, because that's what we suspect is creates the ideal packing, the tessellation. And when we do this, we can again see that first the particles are in a more fluid phase, but eventually they start to align with their faces, and then you can even compress it such that it forms this perfect tessellation. So here it seems like it behaves very similarly to the octahedron, to the dodecahedron. The only thing is that we don't see like a distinct first order transition, but this probably has something to do with the small number of particles that we are dealing with here, with just 24 particles, such that it's hard to identify this first order transition. And the same holds for the radial distribution functions. We can see that they eventually form these 24 cell tessellations, both for the radial distribution function in terms of the center and the vertex, because the 24 cell is self-dual, so they form the same arrangement basically. Okay, so the last particle we are interested in is the tetrahedron, and we see also like the phase transition, which is nice. And here we put 600 particles on this hypersphere, because that's what we expect to form the perfect tessellation, the so-called 600 cell packing. However, what is interesting in this system is if you start to compress it slowly, you can still see that it forms something like a 600 cell. But when you try to compress it to the highest density, what you can see is that it's not perfect. So there's still like some sort of mismatches, and the faces are not aligning perfectly. And you can also see this in the radial distribution function, where the peaks are not really narrow, so they are quite wide, both, and especially here when you look at the radial distribution function according to the vertex positions of the particles. So And if you look a little bit more detail about into this structure, what you can see is that they form like these kind of vacancies. So there are some regions where there's no particle present, but this also means that there has to be some areas where there are interstitial tetrahedra, where the particles are just misplaced. And to look into this a little bit further, I did more simulations by not only looking at the perfect ideal number of particles, but going a little bit below and above, such that you have like an excess of particles or like a lack of particles. And what we can see here is that for the tetrahedron, the perfect, you get like the lowest density or the highest density regime exactly at this perfect 24 particles, which is again the 24 cell, or the 120 cell for the dodecahedra, where you need 120 particles. However, for the tetrahedron, it seems that there is you need less particles to get a more dense configuration. So, but why is that? Well, to look into this, I did also a couple of these kind of simulations, or here's one of them. And you can also see in the radial distribution function that if you only use 580 particles on the hypersphere, you can see that they are way narrower and that they can form a way or something which is way closer to a perfect tessellations. Even though, of course, because you have not all the particles, there are also interstitials in them, but in total they are way more dense. And this kind of integration of defects can be also seen in the critical pressure for the phase transition. When you do this kind of analysis, you can see that roughly at 580, you get the ideal number of, or the lowest critical pressure, which means that the integration of defects somehow aids the phase transition from a liquid phase into the crystalline 600 cell structure. And this in general is very reminiscent of the phase transition for cubes, for hard cubes in Euclidean space, where Marjolijn Dijkstra looked at exactly this kind of phase transition. And she observed that by integrating a small amount of defects, you can stabilize the crystal, the simple cubic crystal, way at even lower pressures. And this is because in the simple cubic phase, you get like these kind of glide planes, and you can easily slide one particle along one of these kind of linear rows, which you can see here indicated in white. And the interesting thing about the 600 cell is that there's something like these kind of rows also present in the 600 cell, which are these so-called tetrahedra loops, so tetrahelix loops, which are on a geodesic of the height on S3. And here it seems like it's also very easy to integrate defects because the tetrahedron can just glide along this tetrahelix. And therefore, integrating defects is less costly as in other crystals entropically. And to look at it a little bit further, we also did free energy calculations by using the Frankel-Ladd method, and compared to an Einstein crystal. And I don't want to go into detail about the equations, but basically what you have to consider is first the free energy of the particles, but also a combinatorial contribution if you have defects present in the system. And what you can see here is that if you don't consider this combinatorial entropy of vacancies, that you get the minimum free energy as vacancy concentration of 0. However, if you consider this contribution, you can see that you exactly get this vacancy concentration, which is non-zero, but a little bit above. And this is exactly around 580, 585 at the critical density where the particles go from a liquid phase into the 600 cell phase. And however, I have to admit that at some point it should go down. So if at higher densities, the minimum free energy configuration should be the one which has no vacancies. However, the way, because I'm doing this simulation in a confined system, because it's on the hypersphere surface, which has a confined volume, the algorithm I applied is such that it can't get rid of these kind of vacancies very easily. And therefore, they're also still present in this high density regime where we try to compress it as much as possible. Okay, so basically this means that we have now covered this first question. Yes, it seems like the tessellations, if there's a tessellation present, that these kind of structures are also entropically favored. But this only, for now, I only really looked at self-assembly in these curved spaces. But what can we now learn from the space, from the self-assembly in curved space about self-assembly in Euclidean space? And for this, again, first looked at the dodecahedron and compared, for example, the radial distribution function of the beta manganese structure, which forms in Euclidean space, to one in the 120 cell. And what we can see here is that the peaks, which are representing the sites on the or the peaks of the 120 cell, are already present in the beta manganese structure. So there seems to be some sort of relation between beta manganese and the 120 cell. But how can we get into this a little bit further? Well, what I try to do is now slowly flatten space by adding more and more particles. Because when you look at the curvature K here, by adding more and more particles to the system and keeping the density, the packing fraction constant, we can then slowly flatten space and get more and more into this Euclidean regime. So for example, for the dodecahedron, instead of adding 120 particles to the hypersphere, we then looked at 300 and even more particles. And we can see if you have 300 particles, you can see that already these kind of peaks shift a little bit and they get even closer and closer to the beta manganese structure, which we see in Euclidean space. And just because videos are also always great, here's one of these videos for 300 particles. We have 300 particles on the hypersphere. And we can see that they form a very dense system at the end of the day. However, of course, they have to integrate some sort of defects. But most of the particles are still aligned face to face with each other. To now look a little bit more detail about the defects and the local environments of each particle, we tried to try to quantify the local environments of these in these crystals by using Minkowski order Minkowski weighted Steinhart order parameter, which is pretty much, like I said, a measure of what is the order between the two of a particle in relation to their nearest neighbors. So basically, what you have to think about here is that each point represents a certain local environment of the system. And because it is, I looked at like a 12-dimensional space in terms of these Steinhard order parameters. Here I represent them in these kind of three different plots. And what we can see, for example, is that the 120 cell, so the ideal environment for the 120 cell, is down here. And for beta manganese, which is in Euclidean, which is the one which forms in Euclidean space, you can see them represented, for example, here or here. And if we now have like a very small excess of particles, we can see that the typical environments spread from the 120 perfect 120 cell environment towards that region, which is also occupied by the two beta manganese Wyckoff sites and environments. So and if we add more and more particles, we can see that they always detach a little bit, but still always originate from this 120 cell configuration. So this means that the particles, there is some remnants of the 120 cell also still present in the beta manganese structure. And we can even go compare this then to the beta manganese, so like a simulation of in Euclidean space for which forms a beta manganese structure. And we can see that they perfectly cover exactly this kind of region, which is also present in curved space. We can even go a little bit further and try to see how these kind of environments evolve compared to the two Wyckoff sites. And what I did here is pretty much I try to assign each individual environment to either Wyckoff site, so this is, I think, 8C or 12D. And then see which one in this Steinhard order parameter space is closer to either 8C or 12D Wyckoff site. And by plotting this, we can see that they start that all the particles are like the 8D or closer to this Wyckoff site, and then it slowly converges to a region which is which we would assume from a self-assembly or the ideal ratio of Wyckoff of these two environments in the beta manganese, which is roughly which is I think 12 to 8. And interestingly enough, based on this assembly, we can claim or make the argument that one of these Wyckoff sites, so this is the 8D, is somehow a remnant which tries to be as close as possible to the ideal 120 cell environment, whereas the other one is the integration of defects into the 120 cell, which means that the beta manganese structure can be seen as a defected 120 cell and is, like I said, a remnant of a perfect tessellation in curved space. For tetrahedra, if we go look at tetrahedra, we see a very similar story evolving here. And like I said here, already in if I give you a quick reminder that the particles don't form a perfect tessellation, but they have like these interstitials and these vacancies because they want to form that at the transition, or they are stabilized by these vacancies at the transition. And if we look at these kind of vacancies in terms of this Steinhard order parameter local environment diagram here, we can see that they also go from the perfect 600 cell towards their closest packing, but they really nicely fit with the local environments of the quasi-crystal. So which means that even in the perfect 600 cell, the typical environments of a quasicrystal are already present, which means that the quasicrystal is probably a result of a very easy integration of defects, of vacancies and interstitials into the perfect 600 cell tessellation. And that also doesn't change when we add more and more particles into in the simulation. You can see that they occupy exactly that space, which is typically also occupied by simulations in Euclidean space, where you get the quasicrystal. And you can also see in the simulation down here that you get like these kind of characteristic pentagon shapes where the particles still try to align with their faces. So basically, what we can the claim here is that the 600 also the quasicrystal is pretty much a remnant of the tessellation in curved space, and here specifically for the 600 cell. But now the question is this true for all the particles? Is this also just we have to look at the like what do they form in curved space in terms of a tessellation, and can we then say, okay, the structure we see in Euclidean space, it's just a remnant of that. Well, for this, to answer this, I looked at the last particle, and that's the octahedron. And if you add so they form the 24 cell, but if you add a couple of more excess particles, you can see that in first glance, they behave very similarly. So most of there are lots of environments which try to be as close to the perfect 24 cell environment. And you could argue that the others up here are defect structures. And you can also see this in terms of the simulation when you look at the arrangement of the octahedra, that they still want to go face to face with each other when they start to crystallize. As you can see here, and you have like face-to-face interactions, but also like these kind of defect structures. However, if you go above 50 or I think 70 particles, so an excess of 46 particles, you can see that the particles are not in the regions, or the local environments are not in the regions of the 24 cell anymore, but they somehow this region is not occupied, but instead they occupy a region which is over here. And you can see this in all of these three plots, that this region of the 24 cell is not occupied anymore. And if you then look at this in terms of the simulation, you can also see that instead of going face to face with each other, the particles try to only occupy one single local environment, which can be also contributed or can be identified as the closest packing. And we compare this, for example, to a simulation of the rhombohedral phase in Euclidean space. You can see that they really nicely occupy this space, but doesn't really have anything to do anymore with the 24 cell. And here that makes sense because compared to the 600 cell and the 120 cell, to flatten the 24 cell, we need to the range between the 24 cell and Euclidean space in terms of curvature is way larger, which means you have to flatten it way more. And therefore, it seems that the strategy of integrating defects becomes less and less favorable, but rather what the particles are then doing, or what entropy is doing, is distributing the geometric frustration, which you add by curvature, to the whole system and to the whole system uniformly, such that each particle has the same local environment. And this is a little bit reminiscent of geometric, a frustrated self-assembly where you have like a self-limiting self-assembly, where, for example, Greg Grayson is studying, where you, for example, have these kind of particles which want to have a certain shape, but the structure they want to form, there's like some sort of mismatch. And that's very analogous to what we have in Euclidean space, where we have shapes which can't tessellate perfectly, but locally they want to align in this perfect tessellation environments. However, they can't because of the geometric restrictions. And for this kind of frustrated self-assembly and self-limiting self-assembly, we can see that depending on the stiffness of the particles, so how much they can be deformed or not, you get like this self-limiting regime, where it is where the deformability is dominating rather than the attaching more particles to the side. However, at some point, if the particles are very, very floppy, it's energetically more favorable to just add more and more particle, which means that pretty much the space they live in wins rather than the shape the shape itself. And it seems like there's some sort of analogy to this hard particle self-assembly as well, where at some point, like if you only have a small number of excess particles, you get it's more favorable to have like this defect integration, where you just add a couple of particles which have not the perfect environment, but by doing this, you can guarantee that all the other, or most of the other particles are still very close to their perfect local environment in terms of the tessellation. And for tetrahedra and dodecahedra, this can be done even until we reach the Euclidean space. However, at some point, the curvature mismatch is so large that we get something similar to this frustration escape, where it's just entropically way more favorable to distribute the geometric frustration uniformly. So to end pretty much this talk, I really quickly also want to go into, want to talk about the icosahedra, because that's pretty much the missing Platonic solid. And like I said in the very beginning, the icosahedra, the perfect tessellation of the icosahedra lives in hyperbolic space. So to do these kind of analysis or similar analysis for the icosahedra, you have to perform molecular or Monte Carlo simulations in hyperbolic space, which I can't do yet. But if you compare, for example, the local environments between the icosahedral honeycomb, which is the tessellation in hyperbolic space, the closest packing, and the simulations of the FCC crystal, which forms in Euclidean space entropically, you can see that it really behaves very similarly to the octahedron, whereas it seems like that we are in this regime where it's just way more favorable to distribute the geometric frustration uniformly and have just one local environment, which then maximizes the entropy. Because when you can see, especially in this plot or diagram, you can see that the particle environments don't really don't occupy the region of the perfect tessellation at all. And therefore, we have two examples where we see the integration of defects with the tetrahedron and the dodecahedron, and two examples where the structures are not remnants of tessellations in curved space, but rather uniformly distribute the geometric frustration. And one way which is showed how to do this is by looking at packings, and that's the reason why the self-assembly and the closest packing are similar in these kind of shapes. And with this, I want to quickly sum up that we have answered now these two questions, that we can minimize the free energy, or tessellations minimize the free energy also in curved space, and we can use space curvature as a tool to regulate geometric frustration. And also, we also have a second answer to the second question, which means that self-assembly in curved space reveals two types of assemblies. One are the assemblies which are remnants of tessellations in curved space, for example, the quasi-crystal phase of tetrahedra, which is related to the 600 cell, or the beta manganese crystal for hard dodecahedra, which is related to the 120 cell. But there are also assemblies which minimize free energy uniformly and have nothing to do with the tessellations in curved space, for example, octahedra and icosahedra. And the question now is this of course only true for hard particle self-assembly, or can we generalize this to self-assembly in general and find always spaces, also if we have like an energetically contribution, that these kind of spaces, if you find a space which has the lowest free energy, can you make some sort of arguments what they want to form in Euclidean space? And yeah, with this, I want to really quickly again thank Schön and Xiaoming and Kai, and all these kind of simulations were done with Whom Deep Blue. And I told Adil already, today we had the release of Whom Deep Blue 4.0. So if you want to start with molecular dynamic simulation or Monte Carlo simulation, now it's the perfect time to get to know it. And yeah, I thank you all for your attention, and I'm open for questions.